In this short video, I will provide an introduction about hybrid analog digital transceiver architecture, which has practical interest for massive MIMO system. Specifically, I will discuss the motivation of this architecture, its differences and possible advantages compared with the conventional digital architecture. Let's start by seeing the basic transmitter and receiver design architecture for the conventional digital communication system. Here we have one transmitter having 3 antennas and one receiver having 3 antennas. As we can see, at the transmitter side, any digital information which is usually taken from a given constellation such as BPSK, QPSK or MRA QAM is first passed through the DSP module, which takes care of all the signal processing tasks including beamforming, precoding, scheduling and so on. The signal which is taken out from the DSP unit will go to the digital to analog converter and then to the up converter using the appropriate modulation, and then it will go to the power amplifier, and finally it will be transmitted through this antenna. The same transmission process is applied in all the other antennas as well. Similarly, at the receiver side, the received signal at each antenna first passes through the low noise amplifier, then to the down converter and to the analog to digital converter, and finally goes to the receiver DSP unit to recover the transmitted digital information. As we know, there is recent interest in deploying several antennas at the transmitter and receiver, which is a massive MIMO system. This system is motivated to boost the channel capacity. To achieve this capacity boost, however, the separation between two antennas may need to be at least λ/2. Thus, when we deploy a massive MIMO system at low carrier frequency bands, the antenna array size would be extremely large. For instance, if we have a 1 meter antenna spacing, we can deploy around 20 antennas by working at 3 GHz carrier frequency, but this number will reach to 400 if we operate at 60 GHz carrier frequency. Therefore, one can think of deploying massive MIMO in 2 scenarios. In the first scenario, we will operate at low carrier frequency bands, for example at 1.8 GHz carrier frequency, which is used in LTE cellular system, and deploy massive antenna only at the base station and single or few antennas at each user terminal, which is shown here, where the base station acts as a transmitter unit and the user terminal acts as a receiver unit. In the second scenario, we will operate at very high carrier frequencies such as millimeter wave bands, which span from 30 GHz to 300 GHz, and deploy massive antenna at the base station and each user terminal. Up to now, we have identified possible equipments and frequency regimes where we can deploy massive antennas. The next natural inquiry, of course, would be to ask whether deploying massive antennas at the base station or user terminal is feasible or not using this digital architecture. In fact, in this architecture, we need to have a separate power amplifier, up converter and digital to analog converter for each antenna at the transmitter side, and a separate low noise amplifier, down converter and analog to digital converter for each antenna at the receiver side. Now, when the number of antennas is large, The cost and power consumptions of the DSP units, the digital interfacing card connecting the ADC and DAC components with the DSP units, and the ADC units will be very high. In general, the power consumption and cost of the DSP units and digital interfacing cards are mainly related to the sampling rate and number of antennas. Therefore, for a fixed sampling rate, which is related to the transmission bandwidth, we expect fairly a linear increase in power consumption and cost in these two units, while still maintaining the desired optimal performance. For the ADC unit, however, the power consumption and price per ADC unit depend not only on the sampling rate but also on its resolution level. And to maintain the desired optimal performance, the ADC resolution should be higher when the SINR experienced at the input of each ADC is lower. The main reason for this is that in the case of a low SINR input signal, the received power at each ADC unit contains weak desired signal and strong interference signal. And to recover the desired signal by the receiver DSP unit, the resolutions of the ADC should be sufficiently large to quantize the desired signal, which is potentially weak. In fact, as the number of antennas is larger, the received signal will likely experience a smaller SINR at the input of each ADC unit in a realistic massive MIMO setup. This is because a massive MIMO system likely operates in a multi-user or multi-stream communication where the number of antennas is much larger than the number of user terminals or streams, which are usually fixed due to the constraints in the channel coherence time. The goal of hybrid analog digital transceiver architecture is therefore to introduce analog signal processing component just in between the power amplifier and up converter at the transmitter side, and another analog signal processing component just in between the low noise amplifier and down converter at the receiver side. By introducing these analog signal processing components at the transmitter and receiver sides, the hope is to reduce the cost and power consumptions of the transceiver unit with acceptable performance loss or without any loss whenever it is possible. With this approach, in fact, one can expect a reduced cost and power consumptions of the DSP units, digital interfacing cards, and ADC units compared to the digital architecture. Of course, this is true if the cost and energy consumptions of the ASP is negligible. The other clear advantage of deploying hybrid architecture is the reduction of the required resolutions of the ADC units. This is possible, for example, by designing the ASP to maximize the input SINR at each ADC unit. In general, one can design or program the ASP unit to achieve different objectives, such as to maximize the SINR at the input of the ADC unit, to maximize the average SINR of all ADC units, and so on. In all cases, the main jobs of the ASP units are to modify and combine the incoming signals according to the desired phase shift and amplitude levels. For this reason, the best approach of deploying the ASP unit is by utilizing sets of phase shifters, variable gain amplifiers, and others. And the phase shift will be used to alter the phase of the incoming signal. The amplifier is used to alter the incoming signal amplitude, and the combiner will be used to combine two or more inputs or intermediate signals. However, since the price of variable gain amplifiers are generally expensive compared to phase shifters, more research work focuses on designing the ASP unit with the help of sets of phase shifters and others. With the phase shifter and other based hybrid analog digital architecture, two types of design principles are adopted. The first one is to apply adders and digitally controlled sets of phase shifters, and with this principle the goal is to design the ASP unit with the minimum number of phase shifters, probably having low resolution. This is because the cost of digitally controlled phase shifters usually increase with their resolution. The second one is to apply adders and predefined phase sets of phase shifters with digitally controlled switches. The motivation of this approach is because the cost and energy consumptions of switches are much less than phase shifters. Under this principle, the goal is to design the ASP with the minimum number of phase shifters and switches. That's it. Thank you for watching this video.